You'll probably notice this tiny air-powered turbine I'm building out of Lego has a pretty strange looking rotor. This rotor is just a few thin wheels pushed together, rather than a typical bladed rotor like this one. And this rotor has some very interesting characteristics. This silly looking rotor might seem like it shouldn't really work, but as we build bigger and bigger versions, and refine the designs of this unique rotor, we'll see that it can actually perform some seriously impressive work. Especially when scaled up like this guy. And of course, it wouldn't be one of my videos if we didn't also build an absurdly powerful generator powered by our biggest turbine. So what's with this odd rotor? Well, today, we're going to explore the fascinating world of Tesla turbines, a special kind of turbine proposed by Nikola Tesla that claims insanely high efficiencies compared to regular bladed turbines. And I'll explain how in a minute. But for now, let's start with our poor man's Tesla turbine made entirely of Lego and see what happens when we power it with some compressed air.
So as the air spirals from the outside of the discs through to the center where the holes are, the air can then be vented out of these two exhaust holes here.
We'll pop an air hose into this hole here, and when I blow into it, you can see the rotor spinning up. But let's use an air tank before I burst a blood vessel. At low pressure, we still get some good speed, and you can see the air being vented out of the exhaust here. Now, let's see what speed we get at 60 psi. Bit of lube so it doesn't weld itself. And there we go, at 18,000 RPM, we're not doing too bad here. At least for a turbine made entirely of Lego. Though, as you can imagine, with a smooth bladeless rotor, speed might be good, but torque isn't great.
Yeah, torque is pretty pathetic.
But there is a way we can massively increase efficiency and torque. I 3D printed these small discs which we can stack close together, and now we have 11 discs instead of 3, so the surface area exposed to the air is much greater. Yeah, not only is torque much improved, but we're also getting over 70% more speed. You see, for Tesla turbines, this unique stacked disc design is what allows it to potentially outperform regular bladed turbines, at least on paper. Instead of air hitting the blades of the turbine, the air sticks to the smooth spinning discs through something called the boundary layer, which is this thin layer of fluid that naturally clings to surfaces, much like the way water will stick to these discs, spinning the turbine. Now this water is pretty turbulent, but the more laminar we can get the fluid, and the faster we can move the fluid, the better we can spin the turbine. And you know what makes for excellent laminar high-speed fluid? Air. Now of course, equally important is how we direct the air around the turbine. Bladed turbines have pretty turbulent flow, but for our Tesla turbine to be efficient, we want the air to travel as smoothly as possible around the discs for as long as possible, imparting as much energy as it can before it's exhausted. As the air imparts its energy to the turbine, it spirals inwards as it slows down, eventually being exhausted near the central axle, which we can visualize here with the smoke. You can see the smoke is moving fastest around the outside, slowing down near the center.
Whew, I'm gonna pass out.
Which is why each disc on the rotor needs holes in it to allow the air to be exhausted. So later, we'll design a housing for the turbine to do just this. For now though, let's continue our mission of building a scaled-up Lego-only poor man's Tesla turbine. For our rotor, we'll use 3 of these Technic gears, which are vaguely disc-shaped and have exhaust vents ready-made for us. Now of course, this rotor breaks all conventions for a true Tesla turbine, having only 3 discs, a rough surface, and the teeth even act as small turbine blades. But I bet we can still get it to perform some real work. This 5-to-1 gear down will also help us to convert speed into more usable torque, and feeding it will be 3 tubes to more evenly distribute the air across the rotor. Let's see if we can still get some okay speed on the output. I bet a real rotor could actually produce some pretty reasonable breeze. But let's go even bigger. Now there aren't many Lego pieces that allow us to make larger suitable rotors, but I wanted to experiment with these large circular plates. Now importantly, you'll notice that these are missing the exhaust vents in them, and they're not at all smooth. So let's see how that impacts the performance. Just how big a deal is it if we don't have thin, flat discs with exhaust vents? What worries me is the slight wobble we can see when the discs are spun.
Yeah.
And yup, as expected, not only do these rotors barely get any speed, but they hit a speed wobble, almost stalling it. And on the speed gun, we can see the speed wobble instantly kills the performance.
Yeah, I think there's a tiny bit of wobble on the rotor, and that causes some massive vibrations when it spins up.
So let's replace these silly Lego plates with some nice, thin, smooth discs with exhaust vents. For this, I'm going to crack out my trusty Bamboo Lab P2S printer. Now, I've been using bamboo printers for over a year now, and these have completely transformed what I'm able to do with these crazy Lego builds. So big thanks to Bamboo for partnering with me on this video. Now at this stage, I don't know how thin I can print these discs, or even what the best material to use is, so I just started with standard PLA, printing 1mm thick discs to make sure they don't shatter at high speeds. These discs will be under some pretty extreme conditions, so I'm just hoping the prints hold up. Well, look great so far.
We'll start with a tiny spacer.
Now between the discs, I'm using 1mm spacers.
Now they're not perfectly evenly spaced, but my theory is that when it starts spinning very fast, they'll straighten themselves out.
I'm curious to see how they perform without a housing, so this Technic frame will direct the air around the perimeter of the discs, but it likely won't help too much.
We'll give the axle just a little touch of lube. You can see as we spin this up, these holes then become the exhaust between each disc.
Gotta say, these discs look so perfectly round and balanced.
Okay, let's run some tests at 40 psi. And feeding it, I've got a 3mm tube going to two 2mm tubes.
Now 2 air jets should hopefully distribute the air to the rotor more evenly than 1. Well, as expected, as the rotor spins up, the centrifugal forces help to flatten the discs out. And because these discs are much larger than our small printed discs, the greater surface area is helping to make better use of the jets of air.
That sounds fast, but not amazing. Let's see what speed we're actually getting.
Though, because it takes a few seconds to build speed, we have to assume torque is still quite poor. And we eventually get around 8,000 RPM. So surely, if we double up the number of discs by printing them even thinner, we can increase the surface area even more? Let's see if this helps. Hey, not only does this rotor reach top speed more quickly, it also spins significantly faster, reaching over 10,000 RPM.
Out of interest, what is torque like?
Well, it's obviously not as torquey as a bladed turbine, but it's better than I was expecting.
It's not bad. It's very weak on startup, but as soon as it gets some speed, it does build some good torque.
So the obvious next step is to see how an enclosure will affect it. I would expect this to not only help to direct the air around the discs, but also to keep the air more laminar and allowing it to spend more time energizing the discs. Let's see. Oh yeah, that sounds much better.
It sounds fast. Okay, let's use exactly the same pressure and see if this enclosed turbine spins any faster. Whoa!
Well, now we're getting another 50% bump to the top speed, which is awesome. We're definitely on the right track. But this got me wondering if the shape of the air inlet to the turbine can be improved. Rather than 2 smaller inlets, what about 1 larger inlet? The air would be a little more concentrated in the middle, but the enclosure should help to distribute the air more evenly as it continues to spin around the perimeter of the housing. Let's try again. Whoa, well, this sounds even faster.
Okay, let's see if our new inlet makes any difference.
There we go, 19,000 RPM. Now messing around with this got me wondering if this rotor might even spin fast enough for it to act like a gyroscope. It's violent and wobbly, but yeah. This is a terrible gyroscope design, but I guess its speed allows us to just brute force it to work. Sorta.
Whoops.
Well, at these speeds, surely this turbine has gotta be powerful enough to power some LEGO contraptions? I built this walker for my steam engine, but I bet this mini Tesla turbine can drive it even better. Now a belt drive connects it to the drive chain, and now when we attach our air, she's off. By the way, if you like experiments like these with LEGO and technology, feel free to subscribe or drop a like, and my Patreon is linked below. Cheers! Even at low pressure, this thing has way more power than we need. So much, it even snapped my driving belts. Twice. Okay, next up, I needed to know which printer filament is best to use for the discs, and how well they'd hold up at higher speeds. So this see-through LEGO housing will allow us to observe these medium-sized discs. I started by printing 16 of these super thin discs at 0.3mm thick, out of standard PLA. Not gonna lie, I'm amazed these printed so well, so thin. They almost feel like paper. Hopefully 16 of these will give us some nice surface area. We'll pop it into the housing here, which is sandwiched between the see-through walls of the LEGO cage, sealing it off. So this one is our PLA rotor, and I'm going to compare it with 5 other filaments to see which one is best. Next up is PLA Tough, which is tougher, and you can see it's less warped than the regular PLA. Then we've got PETG, which not only looks cool and translucent, but could possibly be more durable and less brittle, which is good for something spinning at high speed. And these printed great with surprisingly little warping. Then we've got PC filament in white and TPU filament in yellow, which both need to be absolutely dry. So I blasted them in the AMS2 Pro overnight, which allowed them to both print perfectly with no warping. The PC filament here turned out great, and this is a stiffer material but a bit more brittle, so hopefully it doesn't shatter. And then finally, this is TPU, which is very flexible, so I'm interested to see if it'll straighten out or just flutter around. Okay, let's speed test these starting with our standard PLA rotor. Nice, we reach a top speed of 25.7 thousand RPM, and all tests here are being done with 60 psi. Next up then is PLA Tough, lovely flat and durable discs. Wow, and we hit a top speed of 27.3 thousand RPM. Then we've got PTG.
That I wasn't expecting. I think the pressure dislodged this entire enclosure. Alright, let's try that one more time.
And we hit a top speed of 24.7 thousand RPM. Then our lovely perfectly flat PC discs. Pretty well bang on 27,000 RPM. And finally our TPU, which I suspect might flutter quite a bit. Well, this hit 26,000 RPM, but it vibrated the housing off.
I'm actually surprised how well this TPU stood up. Definitely does feel a little bit wobbly though. More vibration than I would want. Now I'm guessing because these axles have a little bit of flex to them that when they're spinning really fast it creates some vibration which then causes wear and tear.
And actually the vibrations chewed up the axle real quick, so I'm going to rule out TPU. And in the future I'm going to use MTP's lovely metal axles for stability and to reduce wear and tear. Okay, well all of these filaments actually did pretty well, but out of all of them I'm going to go with PLA Tough as I got a good speed and it's cheap and easy to print with very little warping. Now at this stage, I wanted to see if we could perhaps use this turbine to drive a motor like a generator. These noodly dudes can serve as an electrical load, so when we spin the motor, it'll generate a small current lighting them up. Now to give our turbine a fighting chance, we can use this 5-to-1 gear reduction to multiply the torque output by 5. But, as we can see here, even with the gear reduction, the motor is just too stiff to run, and the discs just flutter around.
So during startup, there's just too much friction here to get this thing spinning. And these discs just flutter and vibrate with the pressurized air.
So clearly, we're going to need to build a nice big custom generator for our turbine. And this one is going to be one of my most dense generator stators I've built yet, with 12 poles. When we combine these two Lego discs together, and secure them, yeah, we have my most dense Lego stator yet.
So now we have 12 perfectly spaced holes that we can mount our coils into.
This should really improve the efficiency of the generator.
And the coils will mount directly onto these axles.
We'll then print out a bunch of spindles to wrap our coils onto, and I used 24 gauge wire arranged into 3 groups of 4 coils for our 3 alternating current phases.
This is definitely the most copper I've used in a small generator before.
Then onto our stator they go. If you're curious, here's the winding pattern I used for these 12 coils arranged into our 3 phases. These coils are nice and tight together, leaving almost no gaps between them. So hopefully this will make good use of the magnetic fields that'll pass by them. And speaking of, here's the magnetic rotor, which has 10 powerful N52 neodymium magnets in it. These magnets are 20mm in diameter and 10mm deep and crazy powerful. They should be a damn fine generator.
God, this thing is heavy. There's so much copper and so many magnets in here. Let's give her a little lick.
As is custom, we'll just check it's generating something.
Yeah, it's not bad.
Now because this is a coreless generator, it can start up with very little torque. Even this crappy unhoused turbine can drive it with a gentle breeze, lighting up this LED strip. So, onto our big boy turbine to drive this generator. My goal for this one is to strike a good balance between speed and torque, while being mindful that this is made of Lego. Now here I'm printing 2 different housings for the turbine so we can see which air input nozzle works best. And this is transparent PETG filament so we can just about see the discs through it. And for our rotor, we're going to use 30 of these paper-thin 0.3mm discs made of PLA tough filament, which came out astonishingly flat. I've heard 3D printers have traditionally struggled to print perfectly round objects, making turbines like this almost impossible, but that seems to have been completely fixed by these latest bamboo printers, like my P2S. These discs couldn't be more perfect, and they really do need to be perfect when spun at the speeds we're going to get these up to. By the way, I tested a crazy number of discs here, starting at 1mm thick going all the way down to 0.3mm.
Now these holes around here will act as our exhaust, and we've got exhausts on both sides.
I honestly just never thought 0.3mm would even be possible for such large discs. Though it's quite a heavy rotor, so I'm just hoping it won't shatter at high speeds.
God, even with a tiny push, it just keeps on running.
Now I'm going to test 2 different housings with 2 different air inlets to see which produces more speed and torque. The first one has this fan-like slot shape, and the other splits into 8 smaller inlets. And both aim to spread the air out across the width of the rotor. So let's start our tests with our slot-shaped inlet, and this nice fat 4mm feeder tube. I've got to admit, having destroyed many inventions before, large, fast-spinning things scare me, so my heart was pounding a bit running these tests, which were all run at 85 psi. However, this first one wasn't too nuts. I'm speeding this up a little as it took a few seconds to get up to speed. And eventually we got just south of 7,000 RPM. Not bad for such a large rotor, but a little underwhelming. Next I tried the housing with 8 smaller inlets, and this one definitely fared a little better. Reaching just south of 9,000 RPM. Now at this point I'm sure this would make a good generator, but I still felt we could squeeze more out of it. So I suspected the culprit was actually this tire inflator dude that has a surprisingly small valve in it, much smaller than my 4mm tube. So I upgraded to this nice fat ball valve with a 6mm inlet, which should remove any choke points in the air supply.
Whoa. Sorry, buddy.
And we'll continue with our housing winner, the 8 smaller inlets.
Okay, please excuse the high pitch of this one. It seems to be that when the air rushes through those tiny holes, it does make quite a squeal. I'll try and fix some of the high frequencies in the edit. Okay, off we go again.
I'm being cautious here and just gradually opening the ball valve here in case there's a speed this thing just can't cope with. But at 13,500 RPM at only 85 PSI, I reckon we finally got a decent Tesla turbine here. At least considering this is Lego.
Ooh, I'm honestly a little shaky running some of these tests. With the noise this thing is making, I'm astonished these discs are still holding up. I noticed when I turn on the air, I absolutely can't stall this with my hand. When I hold on as tight as I can... Whoa! Wow!
Well, I think it's safe to say torque isn't gonna be a problem here. But I'd still like to control the output speed so we can vary the voltage as needed. At first I considered a gearbox like this, but there's too much mechanical complexity, and it loses a lot of efficiency through friction in the gearbox.
God, this requires an insane amount of torque just to spin it.
I also considered this smaller gearbox, but worried the gears might strip themselves when changing gears while spinning. Now this cool concept popularized by Brick's master builders seems to be another potential way of varying the output, but I kinda struggle to get it to transition smoothly between the gears. So instead, I took another of their concepts and printed a couple of these cones, and filed them for better grip. By putting two of them beside each other, over here, and here, we can then take a rubber belt, with a low friction guiding pulley, and slide it over both cones. Now when we mount the guiding pulley onto an axle, and pop on a little handle, we can vary the speed of the output. Spin the input, and the lower cone will drive the upper cone. Then if we slide the pulley along the axle, we can essentially change the gearing ratio smoothly to the generator rotor, varying its speed. Then to help friction at the turbine's central axle, I used a couple of these lovely bearings from MTP again, which will pop onto both sides of the rotor. Beautifully smooth. And now, finally, we can hook up our turbine to the generator. Now, I have a suspicion the forces will be extreme, so I'm going to use a metal gear on the central axle, as the small Lego gears have a tendency to break under heavy loads. The larger 36-tooth gear should be okay though. So, let's introduce them to each other. I couldn't wait to run this thing. I used this 3-phase rectifier to convert the AC input from these 3 ends of our coils into a DC output to power some stuff.
Okay, for our first test, let's try these noodles again that we struggled with previously. Well, I don't think it'll take much to light these things, so I'm just going to open up this air a tiny bit.
So, here goes our maiden test. I'm only running this very slowly to check that everything works and nothing wants to destroy itself. This is clearly way overkill for these noodles. But I'll consider this a success in that nothing broke.
I'm not going to open the air all the way up, but let's see what happens if we measure the voltage while putting our foot down on the pedal a little bit more.
The transmission here is set to around halfway, so the magnet rotor should be spinning at a similar speed as the turbine rotor. And we peaked at about 14 volts, which is actually a pretty useful voltage to get to. And again, nothing broke. So let's slide our transmission down to reduce voltage but increase torque. With our multimeter, we can see what the open voltage looks like. And we got about 11 volts. So then what about high speed, low torque? Well, this time the voltage rises much quicker, but I noticed something odd. After turning off the air supply, the voltage actually continued to rise. So clearly this belt is slipping, and it only got better traction after the cone started slowing down. So unfortunately, this tells me the belt transmission is totally crippling our powerful turbine.
Ugh, not only are we losing a lot of torque by using a band, but this band is also disintegrating a bit.
So this belt drive can piss right off.
Okay, I've rebuilt this whole thing here using just gears, no belt drive. I'm still using our 5-to-1 gearing right here to give us some insane torque, which should help us to generate some really good current. Then over here we're using some nice metal gears for extra strength in a 1-to-1 ratio. These two gears can be increased or decreased for extra voltage or current, depending on what we need.
Okay, as a first test of this generator, we of course need to see if it can charge my phone. This app called Ampere tells us how much power the phone is using or receiving. And I also have some supercapacitors in parallel to help smooth the output and prevent massive voltage spikes. Oh, it looks like it peaked at around 14 watts. That's the best I've ever got on a Lego generator.
I've only been running this at about 85 psi, and it could go way higher, but this is about where I'm comfortable knowing this is made of Lego and could explode at any time. Okay, well with this 5-to-1 gear reduction, I'm guessing we might get around 12 volts here, but let's see what we're actually getting.
Guess what? I was wrong. I also forgot to blue tack the damn thing to the table, and it looks like we can very easily hit 30 volts. So of course, I just had to take this massive 100 watt LED panel for a spin, see what she's made of.
And this time I'm gonna properly squish this onto the table. Okay, I've turned the lights down so we can appreciate the LED panel better. Let's give her a try.
Okay, I'm gonna shut up so you can appreciate the sound of this thing.
Well, I was hiding under the desk for that one, but this room definitely got brighter. Gotta be honest, something doesn't smell amazing. I did lube everything up though, and I don't see any damage, so I'm just gonna keep going.
After a quick inspection, I am stunned everything still looks okay. Metal gear is good, bearing is good. Plastic gear has some minor wear and tear, but no need for a metal replacement yet.
Actually, I take that back. There may have been a little bit of wear and tear.
Yeah, that's probably what the burnt smell was.
Okay, now I'm curious to know just how much current this thing's actually drawing. We should be able to read that right here.
Man, this thing is bright. And it looks like we hit a peak of about 1 amp. Not at all bad for this panel. Now because this is a 12 volt panel, and it was drawing around 1 amp, I guess this thing was drawing a total of around 9 to 12 watts, give or take. Well, I'm absolutely delighted with what is now my best performing Lego generator. But are Tesla turbines really all that? Well, if we go back to our first test with the tiny turbine, we can see the Tesla turbine hit 31,000 RPM at 60 psi. But this one is a poorly designed bladed turbine. And at only 40 psi, it not only has much better torque, but it also gets up to 37,000 RPM. Now we're not comparing like for like, and this probably speaks more to my poor designs here, but we'd probably get better performance and efficiency out of a regular turbine. Either way, I had a huge amount of fun with this project and learned a lot. So let me know if you'd like me to build an absurdly powerful bladed turbine in the future. If you'd like to pick up your own bamboo printer or filament, you can use my link in the description, and my designs are available for free on MakerWorld if you'd like to print them for yourself. Cheers, folks!